you to really understand or remember this condition in full, which means that if there is the question boundary condition for normal components of electric flux density, if you just put down the condition for the situation where there is no free charge, it's not a valid reply. So you have to note, for the case of no free charge on the boundary, or put the whole condition. Your questions, please. Well then, we have been discussing the conditions that must be fulfilled at any case in electrostatics on a boundary of two different dielectrics. We of course considered only a plane boundary, but at this condition, those boundary conditions must be obeyed at any case. Now, I will make a short break and wait for your questions. I'm making the break mostly because we are switching to a new topic, and the topic is the principle of superposition. So please ask your questions before I turn the sheet of paper and start a new topic. So far seems that there are no questions. Last possibility. Okay, of course, you can consult with me anytime later, but now we are switching this over. And we start to talk about the principle of superposition. I have mentioned it, by the way, before. We have been classifying media like homogeneous, inhomogeneous, and then we had a classification criteria which was linear and non-linear. And I have mentioned superposition at that moment. So what's that? A superposition means that we can calculate a result of two different causes just simply by adding the result of one cause and the other cause without the presence of the other one. And this is valid and can be done if and only if the media in which the field exists is linear. You remember, we defined linearity like direct proportionality between two effects, for example, field density and field strength. And if this is a linear equation, that is, the permittivity is constant, then we can apply the superposition principle. By the way, this is very important because, as you have heard, we can directly solve only three distinct field cases: point, wire, and plane. And the rest is difficult to solve. And what we can do is to compose more complex cases out of already known elements and add them. So this is the first point. The principle of superposition works. It seems very nice, but The problem is our ability to use it. And I will make an illustration of why this is a problem. Well, first, for example, we would like to find out the superposition of the electric field of the Sun and Earth. So let's say that the Sun is somehow a conductive ball and the Earth is a conductive ball. Well, the radius of the Earth is under 7,000 kilometers. The Sun is some order of magnitude bigger. But anyway, the distance is 150 million kilometers. Those two balls are far, far away from each other. Now, if there is a one charge on the Sun, another charge on the Earth, the common field could be calculated quite easily just by adding, superposing those two fields of Earth and Sun. So I should have another example when this is not so easy. Okay, so what if I have two charged balls? It looks similar. But what if I have two charged balls, one and the other? Those both are small metallic balls. There is plus Q and minus Q. Now, the media around them is linear, so that it strictly follows that superposition principle works. The problem is that we do not know the field of those two balls, because evidently those two charges will attract each other so that the charge will be concentrated here and here. But we only know the field of a charged ball which is sufficiently far from other sources, other charges, so that the charge is distributed with constant density over its surface. Then there is the equation we have already found out. You remember we have been investigating the case of a charged ball which is alone in its own universe. And when those two charges are close together, the principle of superposition still works, just we are not able to use it because we do not know the situation of one or the other source. So we are only able to use the superposition principle for field solution in the case that those sources, those superposing charges, are far enough from each other so that they do not affect the distribution. Or, better to tell, the charged bodies are far enough. So we have defined the superposition somehow. I should possibly show one easy example of a superposition of electric fields to demonstrate that this works. So the first example for superposition would use two charged balls that are far enough one from the other. So we have one ball. It has a radius of A. We have another ball, again with the radius of A. Those two balls are placed in a distance of small d, and the surrounding media has the permittivity of epsilon. We ask a question which is, what would be the electric field strength just at the middle of those two electrodes? And now, to have their any strength we would need some charge. So let's have a positive charge Q plus Q and a negative charge of minus Q on the other electrode. So a simple situation, more or less symmetric, and we would like to investigate the situation just in middle or in between those two bodies. So the superposition principle tells us that we can first calculate the result of the first cause or source, and then we can calculate separately the result of the second source, and then we add those two values, whether for potential scalars or vectors for field strength or field density, and we get the result. So let's do that, for example, for the case of field strength. A charged ball immersed in a media with permittivity epsilon would cause an electric field strength E equivalent to Q over 4 pi epsilon r squared, where r is the distance from the center of the charged ball. Now, that means that the positive charge makes E in this direction on the x. So this is the E1, the electric field strength that would be caused by the first ball at the point of observation. Now for the second ball, we have the same equation, the same distance, but an opposite side of the charge. So the electric field strength of the other one would look like this. And those two field strengths would add and create the resulting field strength E without in this. Now, the only thing we have still to do is to consider that the distance here is d divided by 2. So we substitute d divided by 2 for r and get d squared divided by 4, which cancels with the 4 here, and we get in the point of observation, I would call it, I will mark it somehow like a small rectangle. E is equivalent to Q divided by pi epsilon d square. So this was the E1, in fact, Q divided by pi epsilon d square, but we have two sources that add together, and this is the final value. So we use superposition to establish the field strength in between of two balls, two equivalently charged small balls that are quite distant. Now there is one question that I received many times. How do you measure D? Is that the distance between the centers of the balls? Or is that the distance between the least distant points on the balls, so from here to here? Or is that the distance, like if you measure that by outside? Which of those distances is that? And the reply to that is tricky. The way we have used to calculate the result, that is the superposition principle, is valid only if this makes no difference. So it is valid only if the distance d is so big, so big that compared to the radius of the ball A, it's big enough. Which, as a rule of thumb, is if this is 100 times bigger, you can consider it correct. If it's under that, you have to investigate a little bit. If d over a is less than 5, you got a complete nonsense. So again, we have considered the distance to be much bigger than the radius, and then it makes no sense to distinguish between whether we measure it from the center or from the outer region of the ball. Ladies and gentlemen, are there any questions to this simple use of superposition principle? Well, you will train it a little bit more during seminars, so I will leave it at this point, and as we have still some time, I will quite happily get back to the situation when we use the boundary conditions, because that will allow me to explain also the other thing that seems strange. Why do we have an integration constant when we specify potential? You remember, there always is an integration constant which allows us to shift the value of the potential to any value we prescribe. But why? And I will show you that quite easily. A task to be solved. We have a ball which is conductive and has the diameter of A, or radius of A. And this ball is charged, so that the charge sits on the outer or on the surface of the ball, because the ball has no inner surface. And this ball is then immersed to another ball, to another concentric ball, for example, of glass, which is a dielectric, let's say with a relative permittivity of 4 times more permittive than free space, and then there is free space up to the infinity. Now we should investigate all field values, which is potential, field strength, flux density in this system. So let us have the ball. It has a center. Then there is the other ball around it. The first ball has the radius of A. The second ball has the radius of B. And then we have the rest. And we, of course, for any point of observation, we draw a radius of R. Now we will first derive the equations and then draw a picture of the situation. First, let us start with flux density. So, within this universe, which has inside only a charged ball, a charged metallic ball, an insulator around it, and then free space. As to flux density, there are only two important areas, quite distinct by the way. The first is inside the metallic ball. If you carry out the integration, okay, we still have one important formula. If we create the integration path inside the ball, then we have no free charge inside. Why? Well, because repulsive forces of the charges cause them to sit on the surface of the ball. So if we have integration path which is inside the ball, we do not catch any charges, any free charges, and therefore we have zero. And inside the metallic ball we have zero flux density. Okay, then what would the field strength be? Well, it would be zero. By the way, it's a definition of a conductor, because inside a conductor any field strength would move charges so that they reach a new position where the field of those displaced charges would vanish the original field, and there will be no electric field strength. Otherwise the charges would still move till they diminish the field. So, okay, we have no field or zero field inside the metallic ball. Then, once we get out, we have the integration path, a ball with the center in the center of the universe, of this universe, and a radius r, and integrating outside we will always get the charge q, so that as to electric flux density we would not find any difference between the dielectric and the outer space. Outside of the ball we would still have the equivalent to q over 4 pi r squared. So the flux density will not care whether there is dielectric or not. It would just behave according to this formula. Well, this is not the case of electric field, because the electric field would be zero inside the metallic ball. In the first region with permittivity epsilon 1, it would be E1 equivalent to Q over 4 pi epsilon 1 r squared. And in the second region, outside, with permittivity epsilon 2, it would be E2 equivalent to Q over 4 pi epsilon 2 r squared. So shall we want to picture it somehow, we could start on a new sheet of paper making a graph of those quantities. So we have the vertical axis where all the field values would sit on. We have on the horizontal axis, which is r, we have two important points. Well, A, the radius of the inner metallic ball, and B, which is the radius of the protective insulating glass. So let's make it clear. And now let's draw first the electric flux density. We have established that inside a metallic ball we have zero flux density. Just there is a discontinuity in the flux density. It jumps up to the value Q over 4 pi r, which is a squared. And out of this it goes down 1 over r squared forever. So this is the flux density curve. No change at the other interface, 1 over r squared to the infinity. Okay, now we have the electric field strength, which is again 0 inside the metallic ball. Then on the surface of the metallic ball, so black was the D, now we have E, on the surface of the metallic ball it has some value, D divided by epsilon 1, and it goes down as 1 over r squared, so with the same rate. But suddenly on the interface here we have the equation Q over 4 pi epsilon r squared. So the epsilon now drops down 4 times, which means that the electric field strength jumps up 4 times and then up to the infinity it decreases steadily with 1 over r squared. So we have a discontinuity in the electric field strength, which jumps up so high. So we have pictured 2 of the 3 important actors in this universe and return back to equations. The remaining important one is potential. And as such, the potential has a simple equation in this universe. And it is given by Q over 4 pi epsilon r plus constant. Now important, we have 3 distinct areas: inside the metallic ball, inside the glass insulation, and outside. The potential must be continuous at all boundaries or interfaces and anywhere. So potential must be continuous. Now at the boundary we change the value of the permittivity, and therefore this formula would produce a different result. Fortunately, we have the constant, which we can adjust so that we obtain a continuous potential. To do that, we start from the infinity. So first we establish the potential formula out of the 2 balls. In that case, we have the permittivity of epsilon 2, and it would be quite logic to make world simpler by diminishing this constant to 0. In that case, the potential at the infinity is 0. We have r over any value, infinity. So there's a 0, there's a 0, and there's a 0. So we say K2, which is the constant valid in this area, is 0. In that case, we can return back to our picture and draw the line for a potential. I would try to get a red pencil for that. Okay, so we have a potential that is 0 at the infinity and and somehow from the infinity it grows up to this interface. Now, at this interface, we know that the potential must be continuous, so I do not put here a circle for discontinuity. The potential would be continuous. But we would have to investigate how to make it. Okay, so I would now put down, and in this two, one for the first. So we would have phi 1, which has the same q inside, the same 4 pi and r, but there would be the epsilon 1, and there would be a constant k1, distinct from k. Now we should set up k1 so that the value of the blue potential and the red potential, phi and phi 1, for the radius equivalent to b is the same. So what is required? We tell that q over 4 pi epsilon 2 b plus k, which is 0, skip it, is equivalent to q over 4 pi epsilon 1 b plus k, k1. In this case, we can easily subtract this from both sides of the equation, and we get q over 4 pi b one over epsilon 2 minus epsilon, minus 1 over epsilon 1 is equivalent to k1. Now we have k1 so that the values on both sides of the interface become equivalent, and we can draw a bit more of the picture. So we will continue just from this point. The curve is again 1 over r, but as the permittivity have increased, the derivative is lower, so it would look like this. Now we get to the inner circle, to the inner body, to the ball which is metallic, and within a metallic body we have no electric field strength. Therefore, it must follow that the potential must be a constant. If you derive a constant against radius, you get 0, which is 0 field strength. So the potential here is constant. Okay, now in fact we have the solution. We know that the electric field strength, the potential, and the electric flux density obey the rules of physics in this way. So potential is continuous, but its derivative is not continuous over the interface. Flux density does not care for the interface. And electric field strength jumps up or down depending on the ratio of dielectric constants of the material. So we have solved a simple case, and we have also noted that we will be able to do that only because we can vary the integration constant in the potential equation. Now, there might possibly be some questions.
Excuse me, yes, I have a question.
Yes.
So there is no value then for electric field, yeah, for E on B, on the boundary B line, on the graph.
Which on the
There
boundary?
is no, yeah, like
Well, there is
just,
no value for the electric field strength, because a value for the electric field strength would mean that well, you have a boundary. We had it, well, this is a ball, but let's say we had it like a dividing sheet between two parts of dielectric, E2 and E1. For D, without the presence of a charge, you have a continuous function, but if there is electric field strength, the normal component jumps according to the ratio. So you can't point a value associated with this point, because under it, the value is different than over it. So this is what mathematicians like to draw, like a circle with no interior.
yes,
But
yeah.
yes, those two lines, this and this, go to the very, very proximity. So in fact, they touch each other. Just in the last point between those two graphs, there is a jump.
Okay, yeah, I see. Thank you.
Welcome. Are there other questions? Well, okay. We have done a piece of work. We have established today Laplace equation for potential in a space with no presence of charge. Then we have established another equation similar to the Laplace equation, which is called Poisson equation, which depicts field behavior in electrostatics in a presence of free charge. Then we have solved those equations for simple 1D cases. We have then discussed boundary conditions that connect field at the different boundaries between dielectric materials of different properties.